we should start the lecture now. We are going to study matrix operations today, but before starting this topic, I would like to tell you that I received some feedback about the course and the practicals, and some people were not able to find the topics related to the practical in the course material. So I would just like to show you the place where you can find the presentations and the recorded lectures. So all you need to do is that go to this website, myuni.adelaide.edu.au, and then you need to log in with your user ID, which would be A and then some number after that, and your password, and then you can access the page where you can have the access to all the course material. Then click on the course modules, and over here you have everything related to the course. Okay? I hope most of you know about it, but I recently found out that some people have no idea that there are lectures on this page. So all the whatever we have done so far is here on this page. And if you click on Echo 360, then you can also have access to the recorded lectures. So these are the recorded lectures. Today's lecture is being recorded right now. So for instance, if you want to have access to you want to see the lecture which took place day before yesterday, you just need to click on the green button and the lecture is going to then start. So I hope it's fine. And I would also encourage you to write some notes when I'm teaching, like small bits, just a little bit of hints, so that when you go back home, you have an idea that what were the topics that we studied in the class. And further regarding the practicals, a couple of students, they do not manage to get marked off during the practicals, because what they do is that they do not work on the practical and start working on it right during the practical. Now that's only 2 hours, and I believe, how many students are there normally in one practical? 30, I guess, right? And if the tutor takes about 3 to 4 minutes on every student, like to mark off that student, he needs to ask a couple of questions, check the input and output. 2 hours are over in this time. So if you do not do your practical well in time, you would not be able to get it marked off during the practical session. So just leave only a little bit of things for the practical session. Try to complete the major portion of your assignments before your actual session. Okay? So there is a bit of a recap of what we have studied so far, and the practicals which you get every week are from the topics which I teach during that week, right? So last week I taught functions in MATLAB and how to write your own functions, and that's why we had a practical from functions. And similarly, the next practical is on matrices and Gaussian elimination, which we are going to study today. So when you have a look at the practical, try to recall what we did in the lecture, and I'm pretty sure you would be able to solve the practical. So far we have studied basic introduction to MATLAB, a couple of operations on matrices, then the repetition statements like for loops, while loops, the decision statements, how to do basic input and output, certain functions in MATLAB, writing your own functions, debugging, and logical vectors. So today we are going to do further operations on matrices. Now, I hope from the second lecture everybody remembers what MATLAB was. MATLAB stands for Matrix Laboratory. It was designed to specifically handle data arranged in the form of matrices. So a matrix is an arrangement of data in rows and columns, which is similar to a table. And MATLAB provides a rich set of functions and operators for matrix manipulation and computation. I hope now everybody can visualize a matrix, right? It is like a table which has rows and columns, right? And do you remember what a vector was? What was a vector? So it was like a one-dimensional array, right? So for instance, it may have one row and let's say 5 columns. So let's have a look at this example. A ready-mix concrete company has 3 factories, S1, S2, and S3, which supply 3 building sites, D1, this was supposed to be D2, D2 and D3. Okay, this is D1, D2, and D3. The cost of transporting a load of concrete from any factory to any site is given by the following cost table. Okay, so the first table, it shows the cost of transporting a load of concrete from any factory to any site. Now suppose the manager proposed the following transportation scheme. Each entry represents the number of loads to be transported along that particular route. Now, if we have a look at the factory S1 and the building site D1. So what is the cost of transportation between factory S1 and the site D1? 3, right? This is 3. However, in the second table tells you that how many number of loads are to be transported. For instance, the first cell, the first column and the first row tells you that 4 loads are to be transported between factory S1 and the site D1, right? So the cost of one load is 3. What is the cost of 4 loads? 4 times 3, which is equal to 12, right? So what is happening here is that the first element, the first row and the first column in the first table is being multiplied with the first row and the first column of the second table, right? And we know that in MATLAB we call this element by element multiplication, right? So I made a visual for those who are not here. Let's see if it works or not. It does work. Okay. So what's happening here is that in order to find the total cost, you would multiply 4 by 3, right? And then 0 with 12, and then the next 0 with 10. So this is what we call the element by element multiplication. Okay, so we are back to the video. All right. Now, this represents a solution to the transportation problem. This may not be the cheapest solution, but this is what their manager proposed. So now we want to obtain the total cost of the solution. Okay. So what we needed to do was that we have to do the element-wise multiplication, right? Element by element. And then we need to take the sum. So what we are going to do is that we are going to define a matrix C, which is the first matrix, 3, 12, 10. See, 3, 12, 10, 17, 18, 35, and the last row is 7, 10, and 24. And then the next matrix would be the number of items that are to be transported. And then we are going to perform an element-wise multiplication, which is C dot multiplication times X. Okay? And this is going to give this solution. Now, we basically need to find out the total cost of transporting all the loads between the 3 factories and the 3 sites. So we are going to give this command sum of this total matrix, which is going to return a vector where each element is the sum of each column of total. And then we apply another sum operation to get the final sum of the matrix. Let's see how this happens in MATLAB. So we have this file here. Okay, so I have my cost matrix and then the number of items matrix. Then I take the total. So let me perform these operations one by one. And I'll increase the font size. I always forget that. Okay, so we have 2 matrices now. This is matrix C. Okay, so that you can double click in your workspace and see what is there in your attribute, in your variables. So this is matrix C, and then we have the other one is matrix X. And then we are going to take the total. So now each cell would represent, see we calculated 12 here, so each cell is going to represent the cost of transporting material between any site and any factory. And then we are going to take this sum. Okay, and we take the sum once again, or we have another option, we can take a nested sum. Right, and we are going to get a final answer of 372. So we have seen in earlier lectures too that we use a semicolon to indicate the end of a row when entering a matrix. Bigger matrices can be constructed from smaller matrices. Probably we haven't done this one so far. So we have this a couple of matrices here. A is 1, 2, and the next row is 3, 4. Right? A is 1, 2, and 3, 4. Okay? And B is just 5, 6. So look at D. A semicolon B. What it would do is that it would append, so this was A, 1, 2, 3, 4, and B was 5, 6. So because there is a semicolon, this means we want to add a new row. So B is the new row, okay? Then we have E, where we are concatenating C and D, but over here, there is no semicolon. So what is going to happen? New columns are going to be added. So, so C is, what is C? 7, 8, 9, 10, 11, 12. Right? And then D is going to be added here as 2 columns. If you want to reference individual elements, they may be referenced with a row and column subscript, like A 2 comma 1. So this means the second row and the first column. So we would get, just a second. It should be the second row and the first column, right? Yeah. So it is also possible, let's try this one here. A was 1, 2, 3, 4. Right. Sorry. Okay. Then A 2 comma 1. So yeah, so this should be 3. There is this mistake in the lecture. Okay, this is supposed to be 3 because this is the second row and the first column. It is also possible to use linear indexing where a single subscript is used. So over here we have this 1, 4, 7, 2, 5, 8, and 3, 6, 9. So how many rows are there in this matrix? How many? 3, right? We have 1, 4, 7, 2, 5, 8, and 3, 6, 9. So although it is a two-dimensional matrix, but if you only use a single subscript to access one of the elements in this matrix, what is going to happen is that MATLAB would start counting column-wise. So it would be something like 1, 2, 3, 4, 5, and then the sixth element is going to be returned. And this would happen column-wise from top to bottom, and then left to right here. Okay. Now what about transposing matrices? I believe even students who have not studied matrices in their school have got quite a good idea about basic matrices and operations on matrices. For instance, taking a transpose, where what do we do? What happens when we take the transpose of a matrix? What happens? Yeah, and the columns become the rows. So if you have this matrix 1, 2, 3, 4, let's say, simple. The first row is 1, 2, the second row is 3, 4. If you take the transpose, then columns would become rows and rows would become columns. So we are going to get 1, 3, and 2, 4. And with this apostrophe sign, you can take the transpose of a matrix. The colon operator, it provides an efficient way of handling matrices. For instance, in this following example, you have a 3 cross 3 matrix, but you only want to get which rows? Row 2 to 3 and column 1, 2, 2, right? Although you have a big 3 cross 3 matrix, you are only interested in row 2 to 3, which is, so you ignore the first row, and then the column 1 to 2. Is it 1 to, yeah, it's 1 to 2. So you are interested in this part of the matrix, and then you would get 4, 5, and 7, 8. So you get a small matrix out of it. Similarly, if you write A 3 comma colon, you are telling MATLAB to return the third row, and the colon operator shows that you want all the columns in the third row. And if it is A 3 comma 2 colon end, end means till the end. So you want the third row, and starting from the second column, you want every column after that. And incidentally, we have only 3 columns, so you would get only 8 and 9. And if you want me to show you any of this in MATLAB, then just let me know. Okay. There is something else which is called tiling. Sometimes it is useful to generate a matrix where all the rows or columns are the same. This can be done with the repmat function. So A is 1, 2, 3, and you want to create a tiling of A, okay? And it should be a 3 by 1 tiling of A, okay? So what you are going to get is that you're going to get 3 tiles. So what is A? 1, 2, 3. So imagine this to be a single tile. And then you would get 3 rows of tiles and a single column of a tile, okay? And in the next one, you need a 2 cross 2 tile. So you have now 4 tiles here. 2 rows and 2 columns. What about deleting rows and columns? Does anyone remember how to delete a row or a column? We did it in the first tutorial. We used to make use of the empty matrix, right? So if you, for instance, in this matrix A, if you want to delete the second column, yeah, what you are going to do is that you have to tell MATLAB you want to get rid of all the rows in the second column, so that colon would represent all the rows, and you're going to, what you're going to do, you would write colon, comma, 2 equals to empty matrix, okay? You can also do this by using the logical vectors. Remember, we studied logical vectors day before yesterday. So when you write this logical 1, 0, 1, so only where you see ones, you are going to get those columns, and where you have 0, those columns are not going to be returned. So there are some other elementary matrices, for instance, zeros, ones, random, and I. Remember what I does? If you write I, 3, what are you going to get?
3 by 3 identity.
Yes, good. We are going to get a 3 by 3 identity matrix. And if we multiply an identity matrix with another matrix of the same size, what happens? What is the answer? So you're going to get the original matrix, right? So if you multiply identity with A, you would get A as an answer. Now there are some other things. If sometimes you do need to manipulate matrices. So for instance, in this one, so this diagonal function, what it would do, any idea what it could do? What it should do?
It only keeps the values on the diagonal.
It would give you the diagonal. It will return the diagonal. Okay? It will return the diagonal. So do you know what a diagonal is in a matrix? Those who have not studied matrices. Let's say you have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So anything on the first row, first column, second row, second column, third row, third column, right? These elements are on the diagonal. So this is the diagonal of a matrix. Okay. Then the next one, diagonal pi, 2 pi, 3 pi. This is going to create a 3 cross 3 matrix, and you see you don't have all the elements here. You are not giving all the elements to the diagonal function, so it would create a 3 cross 3 matrix, and the diagonal would be pi, 2 pi, 3 pi, and everything else would be 0. Then you have the flip function, so it will flip the matrix from left to right. UD flips from top to bottom. Then rotate would rotate the matrix by 90 degrees. Now this is not transpose. Remember, in transpose the rows were becoming columns and columns were becoming rows. However, in this one this is not the case. Now if I want to rotate this matrix by 90 degrees, I'm going to get something like this. So this would be an anti-clockwise rotation. Can you see? This is like it moved anti-clockwise. So that 1, 2, 3 now has become 2, 3, 2, 1. And similarly the whole matrix has rotated by 90 degrees. You might need these kind of things when you are going to do image processing shortly, in a few weeks, I believe. The next one is tri L and tri U. So this extracts the lower and upper triangular part of a matrix. So I'll tell you what are those. Now this is a lower triangular matrix, right? So when you have an n cross n matrix, then a lower triangular matrix would consist of this diagonal and everything below it. Similarly, an upper triangular matrix would consist of the diagonal and everything above it. So it's like a triangle in the literal sense. You get a triangle out of it, right? And these kind of things are useful when you are most likely working in graph theory, or maybe if you get a chance to look at the network, friendship network of your Facebook friends, you would get to use these kind of matrices in MATLAB. Okay, now we come to an important topic which is there in the practical as well. It is called Gaussian elimination. Have you studied it before? Like everyone? Okay, great. Everyone has studied it before. If you have not studied it before, let me know. I'm going to explain everything line by line. Or if you have forgotten it, that's perfectly fine. Yeah, okay, I'll explain it. So, suppose we wish to solve the following system of linear equations. These are all linear equations. How do we know? So, because none of these variables, they have a power greater than 1, right? We don't have anything like x squared plus y squared, or we don't have a quadratic equation here. So everything is linear here. What we really want to do is that we want to find out, no more talking, I'm explaining this thing right now. So you have this linear system of equations, and you have three variables in these equations. What are those? X, Y, and Z. And you would like to find out the values of those variables. Now when we're solving these kind of equations, it is important that we have as many equations as we have the number of variables in order to reach to a unique solution. So for instance, let me give you a very basic example. If you have a simple equation which is x plus y equals to 1. Can you find out the values of x and y? Can you give me a unique solution for this equation?
X equals to 2.
Okay. And what is y?
3.
But this is x plus y is 1. Okay, let's say x equals to minus 2 and y equals to 3. But this is not a unique solution, right? So if we want to find a unique solution, we need more information. And we have two unknown variables here. One is x and the second one is y. So we might need some more information. For instance, x minus y equals to 0. And now we can solve this equation simultaneously and reach to an answer. Similarly, when we have three variables, we need three equations to solve this system. So we can solve this system because we have three variables and three equations. However, in Gaussian elimination, what we would do is that it involves eliminating x, which is the first unknown, from all the equations below the first equation, right? We want to get rid of the first unknown in all the equations which are below the first equation. Then, in order to find out y, we need to get rid of y from all the equations which are below the second equation. It is fine if y is there in the first one. And similarly, if we had more variables, then what you needed to do, you need to remove those variables, so the number of that unknown variable below that particular equation, right? Now, I think I should write that equation on the board so that you know what is going on in the next slide. Okay, so your equation is 2x plus y minus z is 8 minus 3x minus y plus 2z is minus 11. And the third one is minus 2x plus y plus 2z is minus 3, okay? Now, for x, we would like to get rid of x from every equation which is below L1. And what we are going to do is that, since we want to get rid of x from this equation, we would make use of the first equation, and we would like to make this 2x, what do we want? We want to transform it into 3x so that it can get cancelled out. And how we would do that? We would multiply this equation by 3 by 2. So if we multiply this equation by the first equation by 3 by 2 and then add it to the second equation, we would get rid of x, because this equation, the first 2x is going to become 3x. And 3x minus 3x is 0. Okay? And then we also want to get rid of this from the last equation as well. And for that, we already have 2x. And over here we have minus 2x. So if we add L1 and L2, these 2x, they are going to get cancelled out. right? This is what has happened in L3. So we are done with the first variable. Now we would like to eliminate y from L3, because the second equation onwards. How we are going to do that? We have 2y in the second equation, and in L3, and in L2 we have y by 2. So we would multiply the second equation by -4, right? So when we multiply the second equation by -4, what is going to happen? That y by 2 is going to become what it would become? -2y, right? And when we are going to add that equation to L3, we would get minus z equals to 1. Is this clear or is it not clear? Not clear? Anyone who thinks it's not clear? Okay, so I'm assuming it's clear. Okay? And now you're going to do some back substitution. So you have your equations in the ideal form where you can solve them. What z is going to be? -1, right? Then you're going to substitute this -1 into L2. You're going to get y. Now you have the values of both x and y. You are going to substitute them into L1, and you are going to get your x. So this is how you would solve in MATLAB. I have it in MATLAB with me. Okay. I'm going to solve this one step by step. So when I have to run a script file, what you normally do, you would write the name of your file, and you are going to get the answer the script is going to run. But so this is how you're going to do stuff in your practicals, and that's how it should be done. But over here, I'm going to do it step by step so that you can see what's going on. So the first matrix would be A. How did I construct A? 2, 1, 1, right? Then -3, 1, 2, -2, 1, 2 from the equations which I had. And then B would be the other side of the equality. If somebody wants to talk, they can go out of the class, because other people are getting disturbed, okay? I mean, it's not mandatory to turn up in the lecture. You can have a look at the recorded lectures. So if you are here, just listen to me what I'm talking about. All right, so we have created the A matrix from these coefficients, and then we create the B matrix from the other side of the inequality. And together, both of them, they are going to make something which we call the augmented matrix. And this is going to look something like this. Okay, so these were your coefficients here, and this is the other side of the equality, which is there in your matrix. So what we first did was that we eliminated x from L2 by multiplying L2 by 3 by 2 and then adding the first equation. So so what we did was that we multiplied L1 by 3 by 2. So that's why AG1 colon means the first row, right? This is what you need to do. And then you have to add the first row to the second row. So then AG2 comma colon, this means that you are picking up the second row. And the result is going to get stored in the second row. Okay, that's why I highlighted it. And then for the third row, what we did, we simply added the first and the third row and stored the result in the third row. Let's do this one here. And then eventually, We eliminated y from L3 by multiplying L2 by -4 and then adding it to L3. So the answer is stored in the third row this time. Okay, so now we have the equations in the correct format, and we are going to do the back substitution. In the back substitution, what we had in the equation, minus z is equal to 1. So z would be equal to 1 divided by -1, right? That minus sign would go on the other side. So this is what we are doing here. AG34 divided by AG33. And at every point you can have a look at your matrix, what is going on in your matrix. Let me show you what AG looks like right now. So this is how AG looks look like right now. And this -1 is that minus z. And this was your 1/2y and 1/2z. Okay? So let's do some back substitution. This is your z. And then you can compute y from z. And finally, you have this x last variable. And you can display the values. So this x equals to 2. Y is 3 and z is -1. So this is the solution of your system, okay? So let's see some matrix multiplication. When two matrices A and B are multiplied together, the result is a third matrix C. So mathematically this can be written as C equals AB. Let's say the size of A is n cross m. This means it has n rows and m columns, right? And then we have another matrix which is of size m cross p. Okay, so we have C equals A times B. The size of A is n cross m. Okay, and the size of B was m cross p. Now these two should be equal if you want to do a matrix multiplication. Okay, so those who do not have a very mathematical background, just remember, so these are the dimensions of your first matrix, rows into columns, and these are the dimensions of your second matrix, and these two dimensions should agree. And then eventually the resulting matrix would be of size this n cross p. So in MATLAB, matrix multiplication is performed with this star operator. So we have two matrices A and B. They both are of equal size. They both are 2 cross 2 matrices. So when you multiply them, you're going to get another 2 cross 2 matrix. And remember that matrix multiplication is not commutative. This means A times B is not equal to B times A. So what's the reason? You know, these dimensions, they would change, and then you may not even be able to multiply them. And so in this, look at the second example. We have the same matrices, but now instead of doing A times B, we are doing B times A, and the answer is different. So finally, for two matrices A and B to multiply as AB, the number of columns of A, they must equal to the number of rows of B. We just discussed that, and in this one the dimensions do not agree. That's why we are going to get an error. Element by element operations are performed by preferring the operator with a dot. I guess we just did a lot of such examples, that whenever you have element by element operations, you put a dot there. And for element by element division, you would do A dot / B. Okay, so let's have a look at the summary. What we did today was that we studied some operations on matrices. We know that MATLAB provides a rich set of functions and operators for matrix multiplications, and these help in implementing many scientific and financial problems. So remember to know the difference between the matrix operations and element by element operations. And it is possible to replace, so we did the for loop thing in the last lecture, so that's it. That's all. And in the next one, we are going to study strings.